George Musser, are you there?
I am here.
It's good to have you on Blogging Heads TV, finally, George. I am John Horgan. I'm an occasional correspondent for science on Blogging Heads TV. I teach at Stevens Institute of Technology. I write an online column for Scientific American. And with me today is a really special guest who I hope will be returning to Blogging Heads often in the future, George Musser. So, George, just tell people a little bit about yourself.
Let's see. I've been at Scientific American now for about 13 years. Actually, I came here shortly after your departure. I guess it was 13 or 14 years ago. And I kind of came here originally as a planetary scientist, as a planetary science guy. That was my original background. And I do a lot of cosmology and astrophysics generally now, and fundamental physics. So anything inside the atom and outside the ionosphere is kind of my domain.
Nice.
Although, please?
Oh, sorry, go ahead.
No, I was just about to say that I had this sneaking interest and love of the most complicated subject in the known universe, which is the human being, the human society, and I think that's far more complicated than anything we'll get into today. But anyway.
That's right. I like to say that compared to neuroscience, particle physics is child's play. I mean, it's just incredibly simple compared to even understanding a single brain cell. But I thought, well, listen, in the future we can get into anything we like. But today I thought we could talk about physics. And my sense is that there might be some colleagues of yours at Scientific American who are actually looking forward to hearing you and me talk, because I get the feeling that we disagree on some things happening in physics over the last couple of decades. Would that be fair to say?
Yeah, we'll have to see what areas of agreement or disagreement we have, and whether they're matters of qualitative or quantitative difference.
Okay. Well, first of all, maybe we could talk about string theory, since that was the topic of a book that you wrote with the wonderful title, I think it's String Theory for Idiots, or Idiot's Guide to String Theory, or tell us a little bit about that.
Complete Idiot's Guide to String Theory. Just hold up the book in front of the video right here. Actually that whole project started as the Complete Idiot's Guide to Quantum Gravity. So it wasn't actually meant to be specific to string theory. It was meant to really discuss the general problem of uniting Einstein's theories with quantum mechanics and creating some kind of unified theory of nature, and the different levels of ambition for that. So I do try in the book to go through some of the different alternatives for that. I should say that my philosophy as a writer and in life generally is to be a connoisseur of ideas. I try to I like ideas. I like to hear about what they are and let them breathe and study them, even if they ultimately prove wrong. And, nature will be the ultimate judge of that. So I did talk primarily about string theory because it does seem to be the main effort to unite the relativity and theory and the quantum theory. But I do go into loop gravity and some of the other approaches as well. Yeah,
I like that, connoisseur of ideas. I actually think of myself in that way too, and I like the idea of giving ideas room to breathe.
Yes.
And yet, I also think it's important to brutally crush ideas at a certain point if they haven't demonstrated any reason why they should continue to be taken seriously. When did you write when was the Idiot's book published?
Well, it came out in 2008, but as you know, it's really, I finished in late 2007. At the time, it was intended to come out when the Large Hadron Collider began colliding particles.
Right.
As you know, it came on and then it had the electrical failure. And anyway.
Yeah. Well, we can get into that as well. Now, what was the timing as far as, there was kind of a wave of anti-string books that came out, and so there was Peter Voigt, who's a prominent string basher. Lee Smolin also seems to have turned against strings. By the way, I think that might be helicopters in the background taking some general...
They're coming for you, John.
Yeah. Well, West Point is right across the river For me, no, everybody up here is, we're all string haters up here, George. So where was your book positioned as far as some of these other critics of string theory?
Yeah, I mean, obviously the publisher and the editor really were interested in the project. They actually approached me about it because of that earlier set of books. I'm not sure if it'd be called a wave, but yeah, the Peter Waite's book. Mm-hmm. And Lee Smolin's Trouble with Physics. Lee Smolin's obviously written a few books of varying degrees of skepticism about string theory. And then, there's been other critics of the theory, including yourself, over the years, so it's hardly specific to Peter and to Lee, but that was kind of the proximate cause for the publisher approaching me, and I have a chapter in the book that kind of tries to pick apart that whole controversy. The string wars, as I think George Johnson called them.
The string wars. All right, let's back up a little bit, and for people who don't follow this controversy closely, why don't you tell us what string theory is and what it's trying to do? So try to situate it in 15 seconds within the context of the great quest of particle physics and physics in general in the 20th century.
Well, string theory's ambition, as I indicated before, is really to provide some kind of unified theory combining Einstein's theories with quantum mechanics and explain the huge zoo of particles we have in nature, and in particular the force of gravity. How does gravity fit in? Because currently it doesn't really fit in. It's kind of grafted on to our current theories of nature. String theory originally began as kind of, the idea was that all the particles in nature, if you zoom in on them, if you zoom in on an electron, quark, those elementary particles, you would reveal the particle to be a small loop or a small bit of some kind of more primordial material. And the vibrations of that material would give rise to the various particles of nature. So if it vibrates one way, I think of it like a guitar string. If it vibrates like an E, it is an electron. If it vibrates like a C, it might be a quark, etc. And as years have gone by, string theory's been fleshed out. It's kind of moved way beyond that original, heuristic picture, conceptual picture of these little vibrating strings. First of all, it includes a lot of other entities of varying dimension that are called branes, as in membrane, of various dimensionality. There's this whole concept that space might be an emergent property of nature, that it's not something that, space is not something that's in the fundamental laws of nature, but it kind of comes out and pops out through certain collective processes, like a crystal comes out of atom and atomic behavior. So
let me just stop you there, because
sure.
You're touching on something that I first heard Murray Gell-Mann talk about. It must have been, 20 years ago. He gave a talk in New York, actually in the offices of John Brockman, the science book impresario and so forth. And I remember, and Gell-Mann brought up this idea of strings actually being more fundamental even than time and space. And I, the question I had was then what, and more fundamental even than matter and energy. And my question was, well, what is a string then? If it's not something that can be situated in space and time, and if it's not constituted of matter or energy, what the hell is it? Is it some kind of pure mathematical form?
Yeah, that's a question people would like to ask. And first, I should say that, in a sense, it doesn't really matter, because science has to proceed incrementally. Some people, of course, would argue that string theory already is a bigger jump than we need to make, so it's premature to talk about what the string might be made of. But there have been proposals for explaining the string as some deeper level even than a string. That might be connected to the idea of space-time foam that John Wheeler always talked about. That, in other words, the string might actually be space and time. And then, of course, you could flip it around and say maybe space and time are somehow the string. So there's a lot of discussion about precisely what is a string, or what are these branes, and how do they relate to maybe more fundamental ingredients of nature.
Okay, so that...
Now, but Gell-Mann really, I think, was getting at, I mean, I wasn't there, obviously. I don't know what he said about this in particular, but what Ed Witten has talked about is that although the usual kind of picture we have in our head of, and even the physicists have in their head of a string and how it vibrates, is that you have some background space, the string is vibrating, moving, whatever, in wrapping around that background space. But actually, the way that the string equations work is that space is somehow derivative. So actually, you define the equations of physics on the string and what's happening in the string, and then you kind of back out from that what the space string has to be moving in to make its motion consistent. So the nice thing about that is a small tweak to what's happening on the string that leads to a radically different view of what the string is doing in space-time. So in that sense, space-time is somehow derivative. And maybe that was what Gell-Mann was getting at. Ed Witten has certainly made that point.
Yeah. Okay, so that is kind of, to me,
I hope I'm making sense.
Well, I mean, these are, it sort of goes with the territory that we might not be making sense right now, because when you're talking about something that precedes space and time, you're talking about something pretty abstract, obviously. But maybe now I should just bring up the issue that I have been, that I've been bringing up ad nauseum for more than 20 years now, which is testability. And that's never really gone away. If anything, from my perspective, the question of testability has gotten much more severe by orders of magnitude over time since physicists like Ed Witten first started talking in a serious way and trying to refine string theory back in the early 1980s. So why don't you address the issue of testability? And there's sort of two issues that people have been talking about for a long time. One is just the basic size of strings, which are down at the Planck scale. This is this extremely small realm that is postulated by particle physics. So just getting direct experimental evidence of the strings is difficult. And then there's also the question of these extra dimensions that are postulated by string theory. So give me your view of the testability issue.
Yeah, let me just pick it apart a little bit, and then we can go back and forth. First of all, I've yet to meet a string theorist, and maybe they're out there, I just haven't had the luck of meeting them, who denies that string theory will ultimately have to be tested. So nature is the arbiter here. Experiment is the arbiter. Ultimately, string theory will live or die based on whether it actually says anything about the empirical data that we have. So I don't think there's any fundamental questioning of how science operates in that sense. It's ultimately an empirical domain of knowledge.
Okay.
So then the question is whether string theory, as we currently understand it, is empirically testable. And I think there's a couple issues to talk about there. One is that this issue of the string being extremely small, 10 to the minus 35 meters or maybe a bit bigger, is not specific to string theory. It's a fact, an empirical fact about the world. The world, in particular, gravity in our world, is extremely weak. And you can just see this through a simple experiment. You take a magnet and a paper clip, and you hold them, and you snap, the paper clip snaps, or the whatever metal you've got snaps up to the magnet. That magnet is pulling the paper clip against the entire mass of the Earth. Electromagnetism is so much more powerful than gravity. It takes not even an entire planet worth of gravitating mass can overcome what that little magnet can do.
Nice. That's a great. I'm going to have to use that in my class.
There we go. So gravity is incredibly weak, and that translates in when you look at the way scales and distances and energies work in nature to whatever is happening between gravity and quantum effects has to be occurring at extremely small distances.
So this is kind of a generic feature of quantum gravity models, quantum gravity theories in general, not just string theory.
Exactly. Exactly. So loop gravity has the same, any gravity theory you care to tell me will have that exact same problem. So this isn't specific to string theory. This is something, it's a terrible fact of nature that physicists have to deal with. So they're going to struggle, whatever theory we have, to come up with some distinctive prediction of quantum gravity. Okay, there's that set of issues. Then, so what can we make of the testability of string theory, or any of these theories, as I've indicated? and that is that any test that we have using current instrumentation, accelerators, photon decay experiments, that kind of thing, will have to be indirect. And so the question is, what kind of indirect evidence might we get for it? And the kind of comparison I make in the book and talk about is that none of them is going to be decisive. None is really capable of definitively ruling in or out any of these theories. And we can get later into what it actually would mean to do that philosophically. But all these tests that are feasible are indirect and partial tests. So a current one that is of some interest is whether supersymmetry, whether there are these supersymmetric particles that are sort of paired off with our existing particles in nature. That's a prediction of string theory. It's some other theories say there won't be that, so it's something that would be able to distinguish those two.
Although it's my understanding that supersymmetry, you can have supersymmetry without strings. Supersymmetry is a feature of some grand unified theories which just unify electromagnetism and the nuclear forces and leave out gravity, right? So you could detect supersymmetric particles at the LHC, and the string theorists would get very excited, of course, because they're so desperate for anything, but that is not definitive.
Right, exactly. So it's a partial, incomplete, indirect test. And so the way I think science works is through that kind of partial indirect test. It's very seldom that you've got ever, in any subject, a definitive test. Sometimes you do, and that's great. But we shouldn't be lulled from those specific cases into thinking it applies more generally. I think of it as sort of like a dimmer switch in my living room. So I can kind of dim up or down the light a little bit at a time. And at some point, it's too bright or too dark, and maybe I'll just go off in another room. And that's kind of how science works. It's going to be, if they don't see it at the Large Hadron Collider, at the energies they're probing, they'll probably dim down the string theory switch a little bit. And if they continue to probe it indirectly and partially, as I'm saying, they'll continue to dim it down. And at one point, the physicists will just, of their own accord, kind of wander off into a brighter room, right. One where the dimmer switch got dimmed up. So,
isn't that already happening, or not yet?
Well, I don't know. I guess I don't see a mass migration, and maybe I'm just missing something. I think one of the important points, though, that Lee Smolin made in his book wasn't so much that string theory should just be rejected or not worked on or whatever, is that the other alternatives need to get some more attention. Right. So, yeah, maybe you are seeing more attention paid to those other alternatives, such as loop gravity or some of the condensed matter analog models or causal sets, or even within string theory, there are sort of paradoxical views of what strings are and what the theory actually says.
Let me just ask you, do you see any of these other candidates in the same ballpark as strings? My sense is that you still think that strings are the leading contender. That's where you would put your money. Loop space theory, any of the other theories that people have bandied about, are any of those really strong contenders in your mind?
I think they're contenders. I don't know. I think they're strong contenders even. I think they're probably all wrong in detail. I think there's something they're all missing. So, but do they introduce new ideas? And this goes back to this whole issue of being a connoisseur of ideas. String theory literally just it might be wrong. Loop gravity might be wrong, but there are aspects of the theories that will then be melded into the more complete theory that everyone's after. So I think all of them have interesting ideas that could be brought into that kind of more deep theory. So that's my own kind of view of the situation. All these other people disagree. One of the difficulties about these string wars, so-called, is that basically few string theorists, or some, really pay much attention to the loop gravity, and most of them don't think very highly of it. And a lot of the loop gravity people don't think very highly of string theory, and it goes back and forth. So I'm kind of standing at really an outsider to this whole discussion, and I think they're all kind of cool, and they all have flaws. So string theory is a beautiful theory. It has a lot of just incredible properties. Same thing goes for the others as well. So I don't know if that's some money putting on kind of thing for me.
Yeah, just going back to testability, and I understand that in many areas of science, you're talking about little incremental pieces of evidence, often circumstantial, very indirect, that over time coalesce into a body of evidence solid enough to sort of tip the scales over to acceptance of a theory. Even quarks, as you know, there's some dispute over whether Murray Gell-Mann, when he originally proposed them, thought that they were real and would ever be experimentally confirmed. He disputes this now, but there's some people who think that he proposed it as a purely mathematical idea that could just help to kind of categorize data coming from accelerators. And then the accelerators became powerful enough that you could get almost like the equivalent of a photographic snapshot of quarks. So the question, cool. So now we accept quarks as a real feature of reality. The question I have, and my assumption, and I've seen nothing to that will change my opinion on this over the last 25 years or so that I've been looking at string theory. My assumption is that that even the hardcore believers in string theory accept that there never will be that kind of photographic evidence of strings, because the Planck scale is just too distant from what we can access with any conceivable physical experiment now. Now, what am I missing there?
I don't think you're missing anything. So, but it's again a question of what we're going to take as evidence for these ideas. So, I mean, barring some kind of real breakthrough, which, as we know, can always happen, it seems to me that the evidence, at least within our lifetimes, will be of this indirect and partial sort. Now, there are, I mean, for instance, here's an example. Suppose the Large Hadron Collider does start to see some of these supersymmetric partners. Suppose. And sees a bunch of them. So it will be able to measure them. Some will have certain masses, charges, other kinds of properties to them. It'll start to make kind of a periodic table of those particles. And so it's something physicists would call a spectrum of particles. That spectrum of particles can be indicative of what's happening at these finer distances, these higher energies. Maybe not all the way down to the Planck scale, but starting to approach it. So there's an example of how you can actually, in some ways, really begin to test these string models. Another example, and this is something that really has been used in the past, and it's actually doesn't get as much attention as I think, at least outside the physics community, as I think it should, and that's these proton decay experiments. So looking for, among just a tank of water, gigantic tank of water, 1 or 2 protons, giving up the ghost every year and just decaying into some more fundamental particles. Just countless, just billions, not even billions. I don't know what the number would be up for these protons.
Zillions, I think is the word.
Zillions, there you go, gazillions even, protons. And, those experiments probe energies almost at the Planck scale. So we already have types of experiments that get at those incredibly high scales. Cosmology presents a lot of those experiments to us naturally. First of all, there are natural particle accelerators in the cosmos that whip up particles to incredibly high speed that, though not quite the Planck scale, are getting up there. The Big Bang, obviously, if we accept the basic picture of a hot Big Bang, early in the universe, particles were at that scale. And we might somehow see the residue of that in the structure of galaxies or in the large structure of space and time itself. So, we're not going to get a picture of a string in the same way we've got pictures of atoms. But we can kind of nibble around it from other angles. So I'm not quite as pessimistic. And by the way, any of these experiments can apply to other theories besides string theory. So no matter what happens, we should be probing these high energy short distances.
Or they could lead to something entirely unexpected, which I think is what physics really needs at this point.
Every physicist wants that. I mean, everybody wants to be the one that comes up with something radically new and that sends them off to Stockholm.
Yeah, I'm sure you recognize this as a science journalist. There are some people, and I hear this from scientists as well as people sort of outside of science, that scientists are so conservative that they try to suppress anything really new and revolutionary. I heard Fred Hoyle, the wonderful British astronomer and physicist, once told me that he thought NASA had discovered viruses and bacteria in outer space, but had suppressed it because it was just too crazy and people would freak out and so forth. And I'm sure you've heard the idea that, there are cures for cancer out there. They're suppressed by the medical establishment. And that idea is so absurd because scientists are desperate for revolutions. I mean, there's some who are more invested in the status quo than others, but in general, scientists, like the rest of us, love novelty. They love to see old ideas overturned and everything up in the air, up for grabs. And I think that what physics needs is, and what it hasn't had over the last couple of decades, except with one exception, one really important exception, is something really exciting and new. The really important exception is the discovery that the universe is accelerating about whatever it was 12 years ago, which really came out of the blue and is by far the most exciting scientific result, I think, of the last 15 years or so.
Yeah, I think most people would agree with you about cosmic acceleration.
But
I mean, obviously, individual physicists might. Suppress is a strong word. It's not like the government suppressing something issue, but they make their individual judgments about what theories are good and bad, and try to convince their colleagues of that. So, on the whole, though, I think there's this love of novelty, and theoretical physics is an idea-rich subject, and that's really that's what's so fun about it, actually.
So back to testability. You addressed the issue of the scale of strings or any phenomenon that can possibly bridge quantum mechanics and relativity. What about the whole landscape multiverse issue? So this really arose, I think, over the last 10 years or so. Leonard Susskind is somebody who's drawn a lot of attention to this. The idea is that, the hope of string theorists, of quantum gravity people in general, was that they would find, Steven Weinberg has put it this way, a kind of logically inevitable theory, a single theory that was so perfect that if you changed it in any way, any of the details, it would fall to pieces. And so all of science and mathematics would be pointing to this one theory. And exactly the opposite has happened with string theory, which is that now you have, the number I see bandied about is 10 to the 500. That's suspiciously round. To me, that number means, like, for all intents and purposes, an infinite number of theories that describe an infinite number of universes with all kinds of different physical constants and forces and types of energy and so forth. And so, in effect, any finding that you get can be predicted by one or another string theory. So again, it raises real questions for testability. So how do you deal with that issue?
Yeah, this is something string theorists, physicists in general, have really struggled with, not just in the context of string theory, but in the context of any theory that predicts or rather allows for just a multiplicity of options and ways things could have turned out. Now, just to clarify a couple things, it's not infinite. It's very, very big, but there's a big difference. In fact, an infinite difference between even 10 to the 500 and infinity. And actually, that was one of the most interesting things about the string landscape concept, was that it does not predict an infinite number of outcomes. It does predict a discrete number, an integer number of possible outcomes, and that is progress. It's better. It sounds kind of almost comical to say it, but to go from infinity to 10 to 500 is a huge step, and arguably bigger than the step of 10 to the 500 down to 1. Mm-hmm. Now, the way you framed the argument, though, is exactly right. The original hope of string theory, the way it was billed, not just to the public, but to physicists themselves, was the goal is, and of unified theories in general, is to find the unique set of equations. You can put a box around them, and everything about our universe will boil down to some feature of those equations, the mathematics of them. And we'll be able to understand why things are as they are, because it mathematically had to be that way. So why do people talk on their cell phones when they're driving? Something that just makes me so angry. It would be because of the equations. I just blame the equations in that case. So, okay.
You're not actually that much. You're not that much of a physics reductionist, are you?
Not at all. No, I'm joking. I mean, obviously, I'm being facetious in that kind of comment.
Sure.
But as you say, the hope was that there'd be this unique set of equations out of everything. It would just emerge from that. It would come in levels, and that's where you would get kind of a contingency. Is at higher levels, you'd have people either able or not able to talk on their cell phone when they're driving. Mm-hmm. Anyway, leaving that aside, string theory didn't work out that way. In retrospect, in 2020 hindsight, it's probably not a surprise that it didn't work out that way, because no other theory in physics does that. No other theory in physics has this kind of uniqueness to it. So take Maxwell's equations of electromagnetism, just the paragonic classical physics description of the world. It explains everything, optics, radio waves, the whole thing. They work perfectly. They're great equations. No one denies it. But they depend on what you put into them. They depend on what charges are, the charge to mass ratio, things like that, the initial conditions you set up. If you do antenna design, there's whole courses on this, obviously, for electrical engineers. Those same equations could describe a huge variety of antennas. A huge variety of every light ray we ever see, every laser beam, every anything, is described by those same equations. There's a huge variety described by those equations. So this is something that happens in physics a lot. Newton's laws of motion describe a huge variety of motion. So that's kind of what happened with string theory.
But wait a minute.
String theory describes a huge variety of universes.
But the kinds of you're talking about a single theory making multiple predictions. That's different from there being 10 to the 500 different versions of Maxwell's equations or Newton's laws of motion or general relativity. Unless I'm missing something in your analogy.
There are a unique set of string equations. So there's something governing the overall universe. Now, what happens in the landscape is that the kind of what I call the bylaws, the local bylaws. So there's this kind of constitution of the land, and then each community state has its own set of laws that have to be consistent with that constitution, with the kind of overall system. So string theory allows for just gargantuan number, but finite number of these local bylaws. And those bylaws will include things like particle content, forces, and so forth. That's where we get this amount of multiplicity. So it's not completely an anything goes situation. There are these overarching principles that govern the whole. And it is possible that individual laws and sets of laws would violate those. So there's some predictivity in that sense. But obviously what we're concerned about are the laws that we observe in the kind of standard model, that there's quarks, electrons, neutrinos, and the whole thing. Those factors would vary. So again, to give another example that actually I kind of like, and this can kind of bring us into other concepts of the multiverse, and that is how planets form. It used to be thought, the Greeks and even Newton and Kepler thought of the solar system somehow a unique geometric structure. Maybe you could form it from platonic solids, for example, and that's why Jupiter is where it's at, and well, they didn't know about Neptune at the time, but all the other planets, Uranus, etc. But that's not turned out to be the case. Planet formation is this kind of very messy process that has a huge variety of outcomes, but it's governed by certain physical principles of a swirling disk and gravity acting on a disk and kind of clumping together matter and so forth. But you could get solar systems out there that have 3 Jupiters, or a Jupiter 5 times the size, or maybe no Earths, or maybe 3 Earths. So that's really been another revolution in science, by the way, that maybe we can have another conversation about in the last 10 or 15 years, is this unexpected variety of planetary systems.
Oh, definitely, because that would bear on questions about the probability of life elsewhere in the universe, too, I would assume.
You bet. Exactly. So something analogous to that is happening with string theory, that there's this possibility, there's certain principles governing the whole process, but they allow for a huge variety of outcomes. And that's what people describe in terms of this so-called landscape.
Right.
So what's interesting is that the landscape itself is kind of a continuum. So there's, again, an infinity of possibilities, but there are a finite number of valleys in the landscape into which a universe might settle.
George, I assume that you've seen some of the things that I've said about multiverse theories. I have fun mocking them and so forth, and I describe it as science fiction with equations and so forth, and I love parallel universe theories, and especially as a plot device for science fiction. When it comes to science, I really see, I reviewed Brian Greene's new book very harshly. I'm not kidding. Now I used to just see this as just kind of funny. Now I see it as something that's actually a problem for science. When obviously a really accomplished scientist like Brian Greene, Leonard Susskind, there are a lot. Stephen Hawking, there are lots of people who now talk about multiverse theory in a serious way. I see this as a problem because, to me, this seems to be a discontinuity in the history of physics. Even though these multiverse theories have been around for a long time, it's the seriousness with which some theorists take them now. That's what I think is different from any time since I've been a science journalist. And I see it as really raising questions about what counts as evidence in science, what even counts as a scientific theory, because I know that there are people who, they still come up with indirect forms of evidence that you could have of parallel universes and so forth, but that is, to me, just seems like pathetic hand-waving, really. So I just want to know how you personally, if it was initially a struggle to accept these as legitimate science, or you never had any problem with them at all, or what your perspective is on multiverse theories, why you take them seriously.
Well, wow, it's a big question, and I should say my own thinking about it evolves. I've gone back and forth in my own thinking between they're great, they're not great, or whatever. So I'll try to give you some of my ideas, but this is just a great conversation to have. And I should say, just as a kind of a meta comment on what you're saying, when a bunch of people I know who are very smart people, Brian Greene, Lenny Susskind, and the other, say something that outright sounds silly. Maybe these guys are just going off, or they're off their medicine, or whatever. But you have to take it seriously. So the very fact that you indicated that you respect the accomplishments of these scientists should make you pause and reflect on your own judgments about this.
Absolutely.
All this is very provisional, and we shouldn't take anything that these scientists say as gospel. God help us. So,
on the other hand, I think
Green,
at a certain point, if you're going to be a science journalist, you have to sort of pump up your ego to the point where you're ready to challenge anyone.
Sure.
Einstein. Einstein didn't think that free will existed. He was wrong, in my humble opinion. It's important to look at some aspects of science from a kind of sociological perspective, and you have to deal with issues of mass psychology and even of what scientists have to do to get tenure and grants and these kinds of political issues. And I think all those factors are coming into play when you're talking about the continued dominance in some circles of string theory and multiverse theories and so forth. That's the only way I can understand it anymore.
Yeah, we can get into some of the sociological thinking later. Here, I think you're right, though. I mean, you have to challenge, you have to question. If you don't believe something, you don't accept something, then ask about it. But I see it as part of a dialectic here. I mean, so it's not just that me, George, or you, John, are just saying, Brian, this is ridiculous. How can you possibly say there's a gazillion universes, or an infinity even of universes out there? Doesn't that go against Occam? And we can make all sorts of, or just, is it just empirically unverifiable by its very nature? And then Brian may have a response, and then go back and forth. And that's how we get to the truth. And so I see it as a conversation that we're having, not a staking out of positions. So this isn't Washington, D.C. We're not trying to say, hey, damn it, we should lift or not lift the debt ceiling as a matter of principle. This is more of a matter of we're trying to have a dialogue and represent a certain position in order to understand it better. That's how I see it, at least.
Yeah, that's absolutely fair. On the other hand, I think, if you look at the history of science, there are such things as dead ends. There are theories
absolutely.
that just peter out, and the bright people just aren't interested in them anymore. I mean, you've got still people out there who practice conventional Freudian psychoanalysis, but they're fringe figures now. Whereas 50 years ago, if you went into the psychiatry, neurology department in any major university, it would be dominated by Freudians.
But how do we get to that deeper and more, hopefully, more accurate knowledge? It's by having these kinds of dialogues and initially take the theory seriously, see where it leads you. And I think, to me, actually, that is where the strongest critiques of the multiverse have come from, is from people like Paul Steinhardt, who've taken it very seriously, and they found that you run into these very deep issues of what probability means in the context of a multiverse. And to me, actually, that's the argument that's the most powerful. It's when people say, well, God, it can't be parallel universes because that's just silly. That doesn't go anywhere.
Oh, I know. I'm agnostic. There definitely could be parallel universes. There could be God. I'm agnostic on God. I'm agnostic on parallel universes for the same, well, not quite the same reason, but because of the issue of experimental access. That's the issue. Not that I think it's a crazy idea. There are lots of crazy ideas that turn out to be true. Quantum mechanics, you cannot get crazier than that, and yet the damn theory works. Multiverse theories, it's another category. I don't see it as scientific because it's postulating things that are just so far beyond the realm of what we can access experimentally.
Right. No, let me just make a couple more comments, and then we can go back and forth. One is, it's not a multiverse theory. There's no such thing as the multiverse theory. A multiverse is an outcome. In fact, maybe there is such a thing as a multiverse theory, but we can immediately, I think, dismiss that. Just all of us can just dismiss that because, as you say, it's starting from just an incredible, postulate that, there's all these universes out there. So the multiverse, the theories that involve a multiverse that we're really talking about, involve it as a prediction of some other principles that, to varying degrees, have been tested or at least are testable. So the obvious one is, there's actually a few, but one is the theory of cosmic inflation, that there was this early hyper-accelerated growth spurt of our universe that accounts for a lot of the properties of the universe we see today. A process that, by its very nature, would result in perhaps an infinity of other universes. So it isn't that we predicted the infinity, it's that we've kind of derived it as an implication of these other ideas. These may be right or wrong, by the way, but we can examine them. We shouldn't criticize the whole thing just on the basis of the existence of those other universes. Right. Quantum mechanics. Now, there's, as you know, 1 or 2 dozen interpretations, so-called, of quantum mechanics. What does the damn theory mean? That's what we want to know. Why does God play dice? Why are these entangled connections and all these just things that just boggle the mind? And one way to make sense of all that is that the quantum mechanics theory, the equations of it, is describing a multiverse. It's basically a theory of the multiverse.
I'm sorry, I was just shutting a window to block out all the goddamn, I don't know if World War III is starting up there or what, but sorry, go ahead.
Well, let's hope we get this conversation over before World War III sets in. This will be our gift to posterity.
And a good one.
Exactly. So you can examine those theories, and there are problems with inflation. There are problems with the many worlds interpretation of quantum mechanics, and you can talk about it. But we've kind of taken the multiverse discussion to a different level, because then we're discussing a theory that is verifiable, and asking what are its implications,
right? And
try to just move forward from there, rather than get hung up on bubbles and other Georges and Johns having the same conversation and stuff like that. I don't know if I'm making any sense.
That is an important distinction. It's funny. I actually just finished reading David Deutsch's new book, and as
good for
I'm
you.
Sure I had to review it for the Wall Street Journal, and I wasn't looking forward to it because I thought it was just going to be another ridiculous defense of multiverse theories or whatever multiverses, and because I know he's a hardcore believer in the many worlds interpretation of quantum mechanics and thinks that it's real and helps to explain quantum computation and things like that. And he didn't really convince me of the reality of many worlds, but he defended it in such creative, fresh ways that I found the book really fascinating and entertaining. But I think it's really a good point to distinguish between a theory like quantum mechanics that happens to imply the existence of other universes according to some interpretations, and something like string theory, the landscape, where the existence of these other worlds becomes more problematic, especially if you're asking the question of why are we in this world? And how can we get rid of the seeming arbitrariness of this world? How can we come up with a theory that, as Steve Weinberg put it, seems logically inevitable?
Yeah, I mean, I think one kind of just bottom line thing we should take away from a lot of this discussion is that the ultimate laws governing physics, should there be those, and we can get into whether maybe there aren't. But if there are, they need not be logically inevitable. That was just a dream of a very specific period in physics, 20, 30 years ago or what have you, and it just isn't working out.
It's older than that. Einstein talked very specifically. He had this wonderful aphorism that the goal of physics is to find out whether God had any choice in making the universe.
Okay, good. Right. So it definitely goes back a ways, and it doesn't seem to be working out. Maybe it will. Maybe the pendulum will swing back, and people have suggested ways to, in string theory, for example, to winnow out the landscape, to say that they're actually not a landscape, it's just one valley. There's different dynamical mechanisms that could eliminate the landscape and explain why we sit in the valley that we appear to sit in. So this is, again, a dialogue that's happening. And, you're getting pushback within physics. It's not just the rest of us saying, whoa, guys, slow down. You're talking about, a huge number of potential universes. The physicists are doing that too, and they're coming up with papers, very specific processes that can maybe bring back some of that earlier hope.
Well, let me, this is great because you really are defending these ideas very well. I'll bring up another thing that an idea that I loved when I first encountered it, because it seemed kind of quasi-mystical, and, I'm an old acid head, and so I really got interested in physics because I thought it might give us some kind of mystical revelation about where the universe came from. And this idea really seemed to be of that ilk. The anthropic principle. So the anthropic principle, the basic idea of it, and it's been around for, 50 years or so. The basic idea is that the universe has to have the structure that we observe. It's addressing this question of the arbitrariness of the world and the laws of nature. And it says, well, the universe has to be pretty much as we observe it, because otherwise we wouldn't be here to observe it. And this has gone in and out of favor it's come back now as a kind of response to this question of, well, if there are all these zillions of universes out there, why do we find ourselves in this one? To me, that's not, there's no content really to the anthropic principle. There's nothing remotely scientific about it. To me, it's just complete circular reasoning, tautology. I'm curious to know what your thought is on it.
I mean, I disagree that it's complete circular reasoning. And one thing we first need to do is to kind of distinguish different varieties of the anthropic principle. Mm-hmm. And there is a strong sense in which people say, well, the universe had to be this way in order to allow for life. And to me, that's just quasi-religious, essentially, crypto-religious. But there's another sense, the weak sense, that I think is extremely useful and does have some bearing on this question of the multiverse. And that is, you think of the anthropic principle as a selection effect. So our existence, we have to take that into account when we look out and do experiments, because we can't observe something that's contrary to our existence. So it's like going back to the planet analogy. Why do we live on Earth rather than on Jupiter? There's no deep reason for that. Jupiter, there's no reason that had the Earth been at Jupiter's orbit, we couldn't live there. But we can't live on Jupiter because it's a hostile environment. We can't live on Mercury for that same reason. So we have to take that into account when we are trying to understand the origin of life. Otherwise, we're going to be misled. We're going to begin thinking any planet can have life on it. And we're not taking an important piece of information that we have, an important selection effect. Now, selection effects are something scientists are always having to deal with. In every domain of science, and this is an example of one, that we exist, therefore our observations are inherently biased by that fact. So you can begin to apply that to the universe as a whole, and you might be misled in the following way. You might be misled in that strong way and say, well, all these parameters that govern star fusion and galaxy formation and everything else, or dark energy and so forth, well, they had to be the values they are to allow for our existence, and therefore we should look for some reason that dark energy has a certain density, for example. So, but then you have to take the selection effect into account and say, well, maybe dark energy didn't necessarily have to have that value. It could have any value. We happen to live in a place where it has the value it does because that is amenable to our existence, and there could be places elsewhere out in deep space that have different values. So that's where I think the compatibility comes in to with the multiverse, this concept of a multiverse. It's not kind of a teleological explanation for our universe. It's just saying, maybe we need to take that bias, that selection effect into account. And people then, to me, it's the usefulness of it is as a consistency check on the multiverse concept. So if inflation, quantum mechanics, what have you, predict a multiverse, we can take a look at the multiverse that they predict and see whether our existence in that multiverse would be probable or not. And if it turns out to be extremely improbable, taking their bias into account, then that would cast some doubt on those theories.
Am
I making any sense at all?
Yes,
I hope this is...
It's still. I mean, it's not telling you anything that you don't already know. That's the problem that I have with the anthropic principle. There's a wonderful cartoon that I saw that somebody says is a great analogy to the anthropic principle. That was published in the New Yorker years ago. It shows a guy who's on a desert landscape, the classic version of the guy in rags. He's crawling along the desert, and there's a sign in front of him, and he's looking at the sign, and there's a little arrow pointing to a dot in the middle of the sign, which is empty, and the arrow says, "You are here." That's what the anthropic principle does. I think it's telling us, yeah, you're here. The laws of nature where you are permit your existence. Like, big fucking deal. I knew that already. I know that I'm alive. I know that nature has to permit my existence. Let me. We don't have a ton of time, and I'm sorry to cut you off because I know you could defend the anthropic principle more. I want to go back to inflation, which you've touched on a couple of times, and its status I find really interesting these days. I started reporting on inflation in the late '80s. I've met the people who were responsible for it. Alan Guth, Paul Steinhardt, and Andrei Linde, the brilliant Russian physicist. And you had a remarkable article by Paul Steinhardt. I wonder if you edited it personally. It came out just a few months ago.
I did. By the way, I loved you had a great description of Andrei Linde in one of your articles from like 20 years ago, where you had him doing cartwheels in Aspen or something like that. I never forget that from my pre-Scientific American days.
He's an amazing person. I haven't heard anything about him in many years, but he was like a performance artist. He was just a really colorful character. But tell me what you make of that. I mean, I thought that basically Paul Steinhardt is pulling the rug out of a theory that he really helped to propagate and make one of the most fundamental ideas of modern cosmology. What was going on there?
Yeah, I mean, I should just give you a quick backstory to that article. So I saw a talk that Paul gave in Trieste in Italy back in, I guess, 2007. And it was raising some of the issues that he then developed into those for the article. And it's fascinating hearing about the difficulties that the theory of inflation presents physicists. It leads them into certain corners, and you wonder how they're going to get themselves back out of those corners. And a lot of it comes down to this question of probability. How do you make sense of probability when you have an infinity of universes? It's just a concept that just kind of falls through your fingers. And it is, as you say, interesting that Paul Steinhardt, who was really one of the fathers of the inflationary theory back with Guth, Linde, and I guess Albrecht and others in the early 80s and late 70s. It is interesting that he is now turning against it. But I should say that Steinhardt himself is somewhat circumspect. He's saying, hey, inflation's got these problems, guys. We need to solve them. His own preference is that maybe inflation could be wrong, but he wouldn't bet his house on that, I don't think. Right. He would say, we've got to deal with these problems. He's held conferences where he tries to bring together people with different sets of solutions. So it's not a rug pulling out kind of thing. It's basically just saying, hey, it's a bell ringing thing. We've got to do something here. It's get the red alert light going on, and let's deal with this problem. And he's also so there's that aspect. And the other thing he wanted to do in that article, he was speaking not just to the general public in the article, but to other physicists who are not aware of this problem and who blithely assume that inflation is a done deal.
Right.
Among cosmologists, among the people who developed inflation, they know better than anyone its flaws. Mm-hmm. It's really the rest of us who've been misled by science journalists and scientists alike into thinking that inflation is a settled matter. It's not. It's a speculative, interestingly speculative theory, but it has its issues.
Well, I've been making fun of it for a long time. I decided by the mid-'90s that I thought it was really problematic, and I couldn't understand why it was so accepted. And the funny thing is that cosmologists talking among themselves were very disparaging about inflation. Again, back even 20 years ago. And bringing up some of these same questions that Steinhardt raised in his article, one of which is very similar to the questions raised about string theory, which is that inflation is this kind of generic idea that is almost infinitely flexible and can predict, if you will, all sorts of different universes. So the issue of testability becomes a real problem. And also what I thought was fascinating was that Steinhardt was saying that the initial conditions required to give inflation in our universe looked like they were actually quite improbable, as opposed to being very likely. And by the way, I'm not sure if we've defined inflation for this audience. So just very quickly, inflation was this idea that emerged about 30 years ago that right at the beginning of the Big Bang, of cosmic creation, the way I understand it, and George, you should correct me if I get this wrong, was that gravity kind of flipped and became a repulsive rather than attractive force, and there was this hyper expansion. It was like somebody put the accelerator down on the expansion of the universe, and just zillions of orders of magnitude of expansion in a microsecond, and then it stopped and became the more leisurely expansion we see now, and that this hyper expansion, now called inflation, could explain a lot of previously puzzling features of the universe. So it became a very, very popular idea, really kind of accepted as part of the almost like a fundamental feature of modern Big Bang cosmology, but really it's always had a pretty shaky basis.
I mean, shaky is probably putting it too strongly. It's interesting theory. It's probably the leading explanation even in its flawed way. So remember, scientists always choose from a Chinese menu of options. They don't just choose, hey, here's the ideal theory. They have to go, is it A, is it B, is it C? And right now there's basically just A. Steinhardt himself has tried to develop a B in this ekpyrotic model of his. Lindy doesn't like that model, and he has his own critiques of it. So it's not like there's a clearly better option than inflation. But it is a fascinating idea. And actually, just tonight, go out and you can make your own simple observation that will convince you of why this is such a big problem. Go out when it's dark, look to your left and look to your right, and look in both directions in space, and you'll notice that space is basically the same in both ways. And why is that? Because at the farthest point in one direction, the farthest point in another, those two places, those two galaxies far out, they've never seen each other. They're too far away. Light hasn't yet gone from one to the other. It's only just reaching us in the middle. So those two galaxies are somehow synchronized in their appearance. And what could have synchronized them? Because light couldn't have done it. Light couldn't have traveled between them. So you need this somehow pre-era of the universe, of our current expansion of the universe. Inflation is a possibility for that. There's also this other ekpyrotic model.
It's interesting because inflation is addressing this question of the arbitrariness of the universe that we've been talking about, that physicists hoped a theory of everything would also be able to dispel. We actually are a little bit over an hour, George, so I want to give you one and possibly big question to close up with. I'm just curious. I'm always curious, asking other science journalists or scientists this question. Do you think it's possible that science will ever really explain the universe so much that we kind of go, okay, I get it? John Wheeler once said that kind of at the end of physics, there would be this idea that just is so beautiful and profound and deeply comprehensible that we go, oh my God, that's it? How could we not have seen that sooner? Like a revelation at the end of science that really explains the riddle of the universe. I just wonder if you think that science will ever come up with that kind of theory.
I do. With qualifications, which I can get into, but yes, I do. And the reason I think that is that there's been a kind of a convergence of scientific theories, really since Aristotle, but certainly since Newton, and all these disparate phenomena of nature. We've been connecting them. So if you just dump all the phenomena of nature we know on the table and we can start to piece them together like Tinker Toys, they connect.
Right. And
it used to be that lightning was thought as profoundly different from light, or profoundly different from a magnet. Now we know those are aspects of the same thing. They've been united with nuclear forces, which we didn't even know about until the 20th century. So there's been this progressive kind of winnowing down. And we're really almost at the end of that particular stage of our understanding. If we're able to unite now the quantum with relativity. So then all the phenomena of nature will come under the same rubric. They'll be somehow shown to be aspects of one another, and we'll have some deeper understanding, because at each time there was a unification, we also had a deeper understanding, and we got, I get it. This is why, electromagnetism works. I mean, you look at Maxwell's equations, they're just beautiful. You look at relativity theory, it's just beautiful how these things all kind of click together. I think we'll get there.
Yeah.
Now, the qualification I should bring to that is it means the end, perhaps, to a certain type of scientific endeavor, namely the search for these deeper laws that link together previously disparate phenomena. But there would obviously be lots of other issues that scientists, arguably more urgent issues that scientists have to deal with as well. So understanding the levels of nature and what happens, as I said at the very beginning, among humans, I think that'll tax us to the very end of our own species' existence. Just understanding ourselves, understanding the details of the cosmos. So, but I do think that there's a convergence of fundamental physics.
That was really eloquently put, George. I think we should wrap it up right there.
Cool. I hope this has been fun. It's been fun for me.
For me too. We'll have to do it again. All right.
Definitely.
I'll talk to you soon, George.
Definitely. Take care.